Hello. Hello dear students, welcome you all. How is everyone? So let us start today's class. So we are discussing all the engineering services previous year's questions. So these questions will be helpful for your GATE preparations also. And if you are preparing for engineering services exams, then also these questions will be helpful. And if you are preparing for state AEJE or central AEJE exams, then also these questions will be helpful to you. Okay. So in shear force, this is the second chapter, shear force and bending moment. So this is lecture number 4 or session number 4 of shear force and bending moment. So let us start the discussion. So in today's class we will be discussing ESE prelims questions from 2007 to 2014. Okay, so these 8 years PYQs on SFD and BMD we will be discussing. Okay, so let us start. Question number 1. This is ESE 2007. Okay. So what are the magnitudes of horizontal and vertical support reactions respectively at support A of the frame shown here? Okay. So here we are having a frame. So now you might be thinking, sir, this is the question of truss. Okay. So why you are solving question of truss in strength of materials? But look carefully in this question. Member forces are not asked. In which member what is the force, that is not asked. Okay, so if they would have been asking the member forces, then it would have been question of structural analysis. Okay, but we can still put this question in structural analysis, but we can solve by methods of strength of materials also. Okay, now what is asked? What are the magnitudes of horizontal and vertical support reactions respectively at support A? So at support A, you tell me how many support reactions will be there. There will be only 2 support reactions. One horizontal support reaction, let us say this horizontal support reaction is HA, and there will be one vertical support reaction, let us say vertical support reaction is V. Okay. Now we have to find out the value of HA and VA. How to find out value of HA? Finding out value of HA is very easy if we do just summation summation of Fx equal to 0. If I do summation Fx equal to 0, I'll be getting value of HA. Okay, so what are all the forces in x direction? So 16 kilonewton in positive x direction plus HA in positive x direction, that will be equal to 0. So HA will be equal to minus 16 kilonewton. That means, what is this minus sign indicating? Minus sign indicating that force HA is in this direction. Okay, we have taken in positive x direction, but actually the force in horizontal direction HA, support reaction HA will be in negative x direction. Okay, magnitude will be 16 kilonewton. So we can rule out these two options. Okay, so either option A or option B will be correct. Okay, now let us see. Here we are having a force of 24 kilonewton. Okay, now this is 24 kilonewton. How can we calculate vertical reaction at A? Simply what we can do, summation of moments, summation of all the moments about point B equal to 0. We can do summation of moment about B equal to 0. From that we can get the value of VA. So summation of moment about B is equal to 0. Okay, so let us see. Because of 16 kilonewton, I'll be getting clockwise moment. So let us take clockwise moment as positive. So 16 into clockwise moment positive, 16 into perpendicular distance is 1.5. So 16 into 1.5. Okay, then plus VA into VA into 4 meter plus VA into 4 minus, see, because of VA also we will be getting clockwise movement, but because of 24 kilonewton we will be getting anti-clockwise movement. Because of this 24 kilonewton we will be getting anti-clockwise movement. So minus 24 into 2 equal to 0. HA will give 0 moment. Okay, so we are not considering that. Now 16 into 1.5 will be 24 plus 4 VA is equal to 48. So VA will be equal to 24 by 4. 24 by 4, that means 6 kilonewton. That means VA is equal to 6 kilonewton. Correct answer will be option B. Option B will be the correct answer. Okay. I hope this question is clear. Let's move on to next question. Next question on your screen, what is the inclination of resultant reactions at A with the vertical for the frame shown in the above figure? Now here is hinge somewhere at point E. So at point E there is hinge. Okay, this is hinge. The distance of this hinge is 2 meters. Okay, so this BE distance is 2 meter and this distance is 0.5 meter as shown here. Okay, now we have to calculate what is the inclination of resultant reactions at A with the vertical for the frame shown. So we have to find out horizontal reaction at A and vertical reaction at A. Now, first of all, you tell me, is this determinate structure or indeterminate structure? First of all, we have to identify if this structure can be solved in strength of materials by using principles of strength of materials or not. Okay, so this structure given here is determinate structure. Why? See, support reactions are how many support reactions? 2 support reactions at A point and 2 support reactions at D point. Okay, horizontal and vertical here, horizontal and vertical here. Total 4 support reactions are there. Equilibrium equations are 3. Okay, so we need one more equation. So one more equation will be given. We'll be getting one more equation because of this hinge. Okay, so we are having 4 equations and 4 unknown. Now, how to find out inclination of resultant reaction at A? How to find out inclination of resultant reaction at A? What we will do, we'll find out RA and we'll find out HA. Okay, RA and HA, these two we will be finding out, and then with the vertical, whatever, so this will be RA, this will be RA, this will be HA. Resultant reaction will be like this. Okay, so inclination with the vertical will be tan theta is equal to perpendicular upon base. Tan theta will be equal to perpendicular upon base. From that we'll be finding out this theta. Okay, so inclination we can find out. Okay, so first of all we have to find out RA and HA. So if I do summation of moment about D equal to 0, if I do summation of moment about D equal to 0, what I'll be getting? Summation of moment about D equal to 0. If I do summation of moment about D equal to 0, I'll be getting RA into 2.5 plus 2.55. Okay, so I'll be getting RA 5 clockwise rotation, okay, minus 50 into 2.5 minus 50 into 2.5 will be equal to 0. So RA will be equal to 25. Okay, because of HA, moment will be 0. Okay, so RA is equal to 25 kilonewton. This vertical reaction at A we have found out. Now let us see HA. What will be the value of HA? How to find out value of HA? If I do summation of moment about E, okay, if I do summation of moment about E, then I'll be finding the value of HA. Summation of moment about is equal to 0, left side. Okay, left side, from left side. Okay, so RA into 2, RA into 2, this will be clockwise, minus HA into this perpendicular distance. So RA into 2, or I can write HA into perpendicular distance is 2 root 3. HA into 2 root 3 will be equal to RA to RA into 2. Okay, RA value is 25. 25 into 2 will be 50. So HA will be equal to 50 by 2 root 3 or 25 by root 3 or 50 by 2 root or 25 by root. Okay, so this is HA. Now, what will be the value of angle? Okay, so this is RA. RA is equal to much? RA is equal to 25. HA will be equal to 25 by 3. This is theta. So tan theta is equal to perpendicular upon base RA upon HA, that will be equal to 25 by 25 divided by root 3. That means tan theta is equal to root 3. That means theta is equal to 60 degree. Theta will be equal to 60. Clear? So inclination of resultant with respect to horizontal, with respect to horizontal is theta. Okay, but they have asked with the vertical, okay. So basically they are asking this angle, okay. So if this angle is 60 degree, theta is equal to 60 degree, this angle, let us say theta dash, this is 30 degree. Okay, so correct answer will be 30 degree. Correct answer will be option C, 30 degree. They have asked with respect to vertical, right? Okay, I hope this question is clear. Let's move on to next question now. If there is any doubt, you can ask me in the comment section. Let's move on to next question. ESE 2008. Okay. A simply supported beam AB of span L carries two concentrated loads W each at points L by 3 from A and B. Okay. So we are having simply supported beam. Okay. And this simply supported beam is A, span is L, carrying two concentrated loads W. Here we are having load W, here we are having load W. Okay, this load is at distance L by 3 here, and this distance is also L by 3. From A also L by 3, from B also L by 3. So this remaining distance will also be L by 3. Okay, so 1/3, 1/3, 1/3. Okay. What is the shear force in the middle 1/3 portion? In this portion, what will be the value of shear force? Okay. Now, because of symmetry, this support reaction RA will be equal to W, and this support reaction RB will be equal to W. Okay. So RA and RB both will be equal to W. Okay. So, okay. Now, if I draw okay, shear force diagram. So because of this RA, I will be getting a jump in shear force diagram here, okay, and that jump will be equal to W. So this value will be constant from here to here, it will be W, okay, W value of shear force here, okay, and then because of this W, shear force will drop by W, okay, so this shear force will become 0, and from here to here, it will be no change, okay, because there is no loading in this portion. Because of this support reaction, it raised by W amount. Okay, then in this region there is no loading, so there is no change in shear force. Here, because of this load W, there is a drop in the value of shear force magnitude by an amount equal to the point load W, and from here to here again there is no loading, so it will remain constant at 0. Okay, then because of this downward loading W, we will be getting again a drop of magnitude W here. Okay, then again in this region there is no, because of no loading, there is no change in shear force, so shear force will remain constant at -W, and here it will shift. Because of this loading, it will rise again by an amount W, so it will become 0. Okay, so in this region, shear force value is, in this region shear force will be, okay, or either you can simply see that if I take a section here, W minus W, resultant is 0. If I take shear force towards the right of the section, okay, this is clockwise W, this is anti-clockwise W, resultant will be 0. Okay, so here in this portion we will be getting shear force. I hope it is clear. Let's move on to next question. Okay, so in the frame shown above, what is the horizontal reaction at left support? So this is right support, this is left support. Okay, we have to find out horizontal reaction. Let us say horizontal reaction is represented by X. How to find out horizontal reaction at this support? Simply summation Fx equal to 0. if I do summation fx equal to 0, what I'll be getting? I'll be getting plus 10 kilonewton minus 3 kilonewton plus h will be equal to 0. So I am taking positive x as positive, negative x as negative. Okay. So h will be equal to 7 kilonewton. Very simple. 7 kilonewton. Correct answer will be option. Okay. Very easy. Next question. What is the reaction at support D of the rigid jointed structure shown above? Okay. So here we have to find out the reaction at support. So this is roller hinge. This is fixed hinge. Okay. So roller hinge means hinge support, but it can move in x direction. This also hinge, but it cannot move in either x direction or in y direction. It cannot move in any direction, but it is free to rotate. Okay. This is free end and 20 kilonewton load is applied at this free. Okay. Now how to calculate what is the support reaction here? Okay. So I can calculate support reaction by considering a minute. Okay. So let us say at this support I am having a vertical reaction RD. Okay, I am having a vertical reaction RD. Here I am having a horizontal support, sorry, horizontal force. So horizontal force of 20 kilonewton is acting at this free end and RD is acting here. Now can I say that summation of moment at this hinge will be equal to 0? Summation of moment at this hinge will be equal to 0. Now moment are coming because of these two forces, this horizontal force and this support reaction in vertical direction. It will not be having any support reaction in horizontal direction because it is free to move in horizontal direction. Okay. So summation of moment at A equal to 0. Summation of moment at A equal to 0. Now summation of moment at A because of 20 kilonewton will be how much? It will be in clockwise direction. So I am taking positive. So plus 20 into what is the perpendicular distance? 3 into 3. 3 into 3, that means it into 6. Okay. Now because of this RD, because of 20, I have written because of RD की वजह से, because of RD it will be in anti-clockwise direction. So I will be taking minus. So minus RD into this is the perpendicular distance, RD into 3, and that will be equal to 0. So RD will be equal to 20 into 6 by 3. So I will be getting 40 kilonewton. Okay. Support reaction at D will be equal to 40 kilonewton. So correct answer will be option D. Is it clear? Okay. So I hope this is clear. Let's move on to next question. So next question is assertion reason question. Assertion. Shearing force may be defined as the rate of change of loading moment. Rate of change of loading moment. A loading moment or bending moment we can consider as same thing because that moment is coming because of loading only. Okay. So shear force is defined as rate of change of bending moment or loading moment. So dm by dx is equal to v. This is correct. This is correct. This is true. Okay. Next, reason. Shearing force at a section is the algebraic sum of the force to the left of the section. So this also in itself is correct. Okay. It can be either to the left of the section or to the right of the section. Both are true. So to the left of the section is also true. So this is also true. But this is not the correct explanation. This is not the correct explanation. So both these statements are individually true, but this is not the explanation of this. That means correct answer will be option B. Both assertion and reason are true, but reason is not a correct explanation of A. Correct answer will be option. Clear? Let's move on to next question. A simply supported beam AB is loaded as shown in the figure below. Okay, so this is the simply supported beam AB. This is loaded here. So loading is 4 kilonewton is the point load acting at point C. This distance is 6 meter, 2 meter, and here we are having a moment, external moment of 8 kilonewton meter. What is the shear force in kilonewton in the portion AC? So what is the shear force? So shear force in AC will be equal to support reaction at A. Yes or no? Shear force in reaction AC will be equal to support reaction at A. Okay, so vertical support reaction at A, let us say it is RA. So if I take any section here and if I consider summation of all the transverse forces to the left of the section, that means I am having only one transverse force, that will be support reaction. Okay, so shear force in AC will be equal to RA. So shear force in AC will be equal to RA, and let us calculate value of RA. RA, how to calculate RA? Summation of moment about B equal to 0. So I can do summation of moment about B equal to 0 to calculate RA. Summation of moment about B is equal to 0. Okay, so if I do summation of moment about B equal to 0, I'll be able to calculate RA. So moment about B, because of RA, I'll be getting clockwise rotation. Clockwise rotation, so let us take clockwise positive. So plus RA into what is the perpendicular distance? 6 plus 2, 8 meter. So RA into 8. Okay, now this is 4 kilonewton. 4 kilonewton. This is giving me anti-clockwise rotation. So minus 4 into 2 minus 4 into 2. Okay, then I am having one moment here also, and it is also clockwise, plus value of this is 8 kilonewton meter plus 8 will be equal to 0. So from this I can calculate the value of RA, that will be equal to 4 into 2, 8. So minus 8 plus 8, they will both will cancel out. Okay, so RA will be equal to 0. RA, support reaction at A is 0. So when support reaction at A is 0, that means shear force in AC also be equal to 0. Correct answer will be option, right? Correct answer will be option C. Okay, clear? I hope this question is clear. If you are having any doubt, you can ask in the comment section. Let's move on to next question. So which one of the following is the correct bending moment diagram for propped cantilever beam shown in the given figure below? Okay, so here are the options for bending moment diagrams. Okay, so first of all, how to eliminate these questions are best solved by elimination method. Whatever option you are seeing, okay, you can reject right away. Okay, by that selection by rejection method. Okay, first of all, in this region I will be getting linear bending moment diagram. In this region I will be getting linear bending moment diagram. In this region also I will be getting linear bending moment diagram. Okay, so linear or triangular. So in all the three portions I will be getting linear or straight line or triangular bending moment diagram. Linear, straight line will be there. Okay, so first of all I will reject all those options which are having curved. Okay, so this is straight away rejected. Then at this portion, at this section, my bending moment will be equal to 0. Bending moment will be equal to 0 at this location. So because of bending moment given here, okay, this is also rejected. Okay, now there are, see, these two are similar bending moment diagram. Okay, similar, shape is similar. The only difference is that the magnitude here is 30 kilonewton meter, magnitude here is 15 kilonewton meter. Okay, so out of these two, now I just have to see if my bending moment value at A is 30 kilonewton meter or 15 kilonewton. Okay, this distance is 1 meter, this distance is 1 meter, this distance is 1. Okay, now you just see, if I want to draw the bending moment diagram, how can I draw the bending moment diagram? Just see, in this region here, from here to here, it is 30 into perpendicular distance. Okay, so here I will be getting value 30 into 1 and it will be negative. So I will be getting bending moment diagram value, bending moment diagram as 30 into like this. Okay, now at this location bending moment will be 0. At this location bending moment will be 0, and from here to here, entire portion, this entire portion, I will be getting a straight line. Okay, so if I see similar triangles, if I solve by similar triangles, what I will be getting, okay, here the value is 30 kilonewton meter. Okay, this distance is 1 meter, this distance is 1 meter. Okay, so if this distance is 1 meter, this value is 30, this distance is 1 meter, this will also just by similar triangles I can see that by using similar triangles, this is 30, if this is 30, this will also be 30. Okay, so correct answer will be option A. Option A will be the correct answer. Clear? Okay, so let's move on to next question. If you want to solve, you can solve also. Okay, this will be 60 kilonewton. This support reaction will be 60 kilonewton if you take summation of moment at B equal to 0 or bending moment at B equal to 0 from this side. Okay, so this way you will be getting it as 60 kilonewton, and by solving also you will be getting 30. Okay, now next question. A beam of uniform flexural rigidity supports a set of loads as shown in figure below. So here I am having 10 kilonewton load, 2 meter is the overhanging portion, 4 meter is the distance between simple supports, and again here 2 meter is the overhanging portion. 10 kilonewton is the load at this free end, 10 kilonewton load is the at this free end. Okay, and central point load W is acting. Okay, so this is the loading beam in loaded condition that is given. What is the value of W? We have to find out W. If the magnitudes of bending moment at midspan, magnitude of bending moment at midspan and at support of the beam are numerically equal. So bending moment at this portion, bending moment at this portion and bending moment at this portion, these are numerically equal. Now at this location, value of the bending moment will be minus, negative. Okay, because this 10 kilonewton will be giving hogging bending moment. This 10 kilonewton will be giving hogging. Okay, so here I will be getting negative. Okay, and because of R, what will happen? Because of R, what will happen? This will be giving me positive. Okay, so here I will be getting positive bending moment. But whatever is the magnitude of negative bending moment here, same magnitude of positive bending moment should be here. Okay. Now to calculate value of negative bending moment, it is very easy. Okay, let us say this is M1, this is M2. So M1 will be equal to, I just have to consider the numerical value. I am taking mod. Okay, numerical values are equal. So this is negative, but I am taking mod. So it will be equal to 10 into 2. So mod 10 into 2, that will be equal to 20 kilonewton meter. Okay, so M1 numerical value of magnitude, numerical value of bending moment at this section, this location is 20 kilonewton meter. Okay, now here also magnitude should be 20 kilonewton meter, but in order to calculate magnitude here, I have to calculate support reaction. Okay, so support reaction will be equal to 10 plus W by 2. Because it is symmetrical, total downward loading is 20 plus W, this will be half. So 20 plus W by 2 will be equal to 10 plus W by 2. 20 plus W whole upon 2 will be equal to 10 plus W by 2, right? Now bending moment at 2, M2, that will be equal to minus 10 into 4, minus 10 into 4 plus R into 2. Okay, now M2 will be equal to 20 kilonewton meter. Okay, this will be positive. So 20 will be equal to minus 40 plus R into 2. Now what is the value of R? Let me write here again. So 40 will come here, it will become 60. 60 will be equal to 2R. R will be equal to 30. What is the value of R? 10 plus W by 2. So 10 plus W by 2 will be equal to 30. So W by 2 will be equal to 20. W is equal to 40 kilo. Okay. So this load W will be equal to 40 kilonewton. Correct answer will be clear. Is it clear? Any doubt? Shall I repeat? If you want to repeat, I can repeat also. But anyways, let's move on to the next question. I hope this was clear to you. Just a minute. Okay. So next question. A simply supported beam is loaded as shown in figure below. So this is the simply supported beam here. The bending moment at point C. So we have to calculate bending moment at point. Okay. Now how to calculate bending moment at point C? What we can do? We can we can split this beam into two parts. First part, let us remove this end moment. Let us remove these moments and just let us calculate bending moment at midspan because of central loading. So this central loading is 4 kilonewton. 4 kilonewton. Okay. Now what is the bending moment at midpoint here? So bending moment at point C will be equal to PL by 4. PL by 4. This formula you should remember. Okay. So it is PL by 4. What is the value of P? P is 4. Length is 4 divided by 4. So it will be equal to 4 kilonewton. Okay. So bending moment at C because of central point load alone will be 4 kilonewton meter. Okay. Now it will be sum of these two plus. Now I'll remove this loading, remove this point load, and I'll apply these two loadings. Okay. So these two moments basically, I'll apply these two moments, equal and opposite moments. Here 4 kilonewton meter, here 4 kilonewton. Okay. So bending moment at C here, it will be, now these will be giving hogging bending moment. Okay. So hogging bending moment and constant bending moment throughout the beam. Constant bending moment minus 4 kilonewton meter. If I add these two, this 4 kilonewton meter plus minus 4 kilonewton meter, I'll be getting bending moment at C final will be equal to 0. At point C, bending moment will be equal to, right? So correct answer will be option D. Option D is the correct answer. Okay. Let's move on to the next question. Shear span is defined as the zone where shear span is defined as the zone where shear force is. No. Okay. Let's move on to the next question. A simply supported beam AB is subjected to a concentrated load at C. Okay. So we are having a simply supported beam. Simply supported beam AB. This is the simply supported beam AB subjected to a concentrated load at C. The center of the span. C is the center of the span, and here we are having a concentrated load. The area of shear force diagram from A to C. Let us say this is P. Okay. Shear force diagram will be this. This will be the shear force diagram. This is P by 2. This is L by 2. This is L by 2. And this is P by 2. Okay. This will be negative. This will be. Okay. So this is the shear force diagram, right? And this is the loading diagram. The area of shear force diagram from A to C. So area of shear force diagram from A to C means this much area. What is this area? Okay, what is this area? Now I have already told you dm by dx is equal to shear force at any section. Okay. Now if I take this dx here, so dm will be equal to vdx. Okay. And I integrate this. If I integrate this, what I will be getting? Integration of dm will be moment, and I am integrating from section 1 to 2. Let us say this is section 1 and this is section 2. Okay. So integration of moment from section 1 to 2 will be from m1. At this section bending moment is m1, and at this section bending moment is m2. Okay. So it will be m2 minus m1. M2 minus m. And that m2 minus m1 will be integration of vdx. So integration of vdx will be giving this area. Okay. Area of shear force between 1 and 2. Now what are these two? See, now this much is clear. Area of shear force between any two sections, area of shear force between any two sections in shear force diagram, okay, that will be equal to change in bending moment between these two sections. That will be equal to change in bending moment between these two sections. Okay, this is clear. Now here I have to take sections as A and C. Okay, here in this particular question I have to take sections A and C. So from A to C, this area will be giving me change in bending moment from A to C. So difference between bending moment values at A and C, right? Correct answer will be option D. Option D is the correct answer. Okay. But one thing to notice is, at A, bending moment is 0. Bending moment is 0 at A. Okay. So difference in bending moment values at A and C will be equal to bending moment at C, yes or no? Will be equal to bending moment at C. So this will also be correct. But in engineering services, only one option is correct always. Okay. If this would have been gate examination, then we can then the correct answer will be A and D, because in gate MSQs are also asked. But this is not an MSQ question, this is an MCQ. Since this is an MCQ question and two answers are correct, we have to choose which one will be the appropriate, which one will be the most appropriate. So this option is specific for this condition only, but this option is general, it is valid everywhere. So which one to choose? D option we will. Okay. So although A is also correct and D is also correct, both are correct, but we are choosing option D because it is more wide application. Okay. Let's move on to the next question. I hope this is clear. Let's move on to next question. The shear force diagram is as shown below. So here a shear force diagram is given. Loading diagram we have to calculate. So loading diagram, here we will be having point load. Just by looking at the shear force diagram, where there is sudden change in value of shear force, we will be getting a point load or support reaction. Here also we will be having a point load, there is sudden change. Okay, so point load again. Here also we will be having a point load or support reaction. Point load or support reaction. Here also point load or support reaction. Okay, so at point A, B, C and D, at all these points, either we will be having a point load or a support reaction. Okay, so point load, point load, point load, point load, point load. This option is wrong. Okay, point load, no point load here, or option is wrong. Point load, point load, point load, point load. Okay, so two options we have directly eliminated. Now, next part, no loading in this part. In this part, no loading. Okay, in this part, shear force is constant, no? When shear force is constant, there is no transverse load. Okay, so no loading. Shear force is constant means there is no transverse load. Okay, so here no loading, here no loading. In this portion, shear force is changing. So when in this portion, let us first reject one or two more. No loading in AB and no loading in CD. No loading in AB, no loading in CD, no loading in AB, no loading in CD, no loading in AB, there is loading in CD. Okay, so this is wrong. Okay, so three options are eliminated. We are having answer A, option A as the correct answer. So no need to calculate the magnitude of reactions. Okay, without even calculating the magnitude of reactions, you will be able to get the correct answer. Okay, and in this portion BC, in portion BC, there is a straight line, inclined line, triangular shear force diagram. That means we will be having uniformly distributed load in. Okay, option A is correct. Clear? No need to calculate values, magnitudes and anything. This question. Now let's move on to the next question. The correct bending moment diagram for the column is. For bending moment diagram of column, we will be drawing here vertical. Okay, so let me draw the reference line first. Okay, let me draw the reference line for column first, and then okay, so here we are having support reaction. Here we are having reaction. Okay, here we are having support here. See, in this type of question, what you can do, this is acting like a simply supported. Okay, it is simply supported. What it will act like simply supported because it is simply supported. Okay, this hinge, if you take this much part away, this part will also act like a simply. Okay, for this much part, what it will give, here bending moment will be 0, here also bending moment is 0, here also bending moment is 0. This is providing a support reaction here in horizontal direction, this is also providing a reaction here. Okay, not support reaction, but still it is providing a reaction here because there will be reaction at hinge. Okay, so it will be providing a reaction here. So if I separate this part, what I'll be getting, a simply supported beam like this. Okay, here this, like this. Okay, now in this part, remaining part, whatever reaction was here, same reaction will be here. So it will act like a cantilever like this. So bending moment diagram will also be like that only. Here bending moment will be 0 at this location, and in this part bending moment will be just like a simply supported. Okay, so bending moment diagram in this part will be right. So bending moment diagram will be like this. This will be the bending moment diagram for this part, just like a simply supported beam. And here bending moment diagram will be like a cantilever. So correct bending moment diagram. This will be linear straight line. So it will be like this, continuing like this. The bending moment diagram will be okay. So here at the level of hinge, bending moment will be 0, and here I'll be getting negative bending moment at this fixed end. Here in this portion I'll be getting positive bending moment, and if you want you can. Okay, so this will be the bending moment diagram. Thank this they have correctly this. Okay, okay, all the shapes are correct. All the shapes are correct. No shape is wrong. Okay, so we have to find out magnitude in this case. So how to find out magnitude in this case? We have to find out magnitude. So here the value will be p by 2. Here p by 2. Okay, so this will be p by 2 and p by 2. Why this is p by 2? P by 2 because P load is acting here. This and this. Okay, here we will be having equal. Okay, p by 2 and p by 2. These are the support reactions. By 2 by 2. So what will be the value of bending moment here? The value of bending moment will be PL by 4. This value will L by 4. Okay. Now, if I consider similar triangle, here this is PL by 4, this length is L by 2, this length is L, this length is L. So I'll be getting PL by 2. This is L by 2, PL by 4. This is L, so PL by 2. This will be PL by 2 by similar triangles. Okay. So PL by 4, this should be PL by 4, and it is PL by 4. It is not I, it is L. Okay, correct answer will be option. Any doubt? Any doubt? Okay, so let's move on to the next question. A freely supported beam AB of span 4 meter is subjected to a UDL of 1 kilonewton per meter over the full span and a moment of 2 kilonewton meter at support A as shown in the figure. The resulting bending moment at mid-span of the beam will be. Okay, so this is freely supported beam, that means simply supported beam. Okay, this span is 4 meter, it is subjected to UDL. UDL is 1 kilonewton per meter, and we are having 2 kilonewton meter like this. Okay, so we have to find out the resulting bending moment at span C. So in order to calculate bending moment at C, we can either find out bending moment at point C from right side or from left side. Okay, so let us find out from right side because I think it will be easy. So first I have to calculate support reaction at B. I have to calculate support reaction at B, RB. Okay, how to calculate? I can do summation of moment about A equal to 0. I can do summation of moment about A. If I do summation of moment about A equal to 0, I have to consider RB, UDL and this moment. All these three I have to consider. Okay. Now, because of RB, I will be getting negative anti-clockwise. So minus RB into perpendicular distance is 4 meter. So minus RB into 4 meter plus at this location bending moment due to UDL will be equal to WL square by 2. It will be plus. Why plus? Because of this we are getting clockwise rotation. So plus W, what is the value of W? 1. So 1 into L square by 2, 4 square by 2, 4 square by 2, okay. And here this is anti-clockwise, so minus 2 will be equal to 0, okay. So 4 RB will be equal to 16 by 2, 8 minus 2. So RB will be equal to 6 by 4, that means 3 by 2, that means 1.5 kilo. RB, support reaction at B, RB will be equal to 1.5 kilonewton. Okay, very good. Now, if I have to calculate bending moment at C, if I have to calculate bending moment at C, bending moment at C will be equal to minus RB in minus RB plus W into x square by 2 plus W into x square by 2. Okay. Perpendicular distance of RB, oh, but I have to take bending moment. So for bending moment, RB will be giving me positive bending moment because RB will be giving me sagging bending moment, and this UDL will be giving me negative bending moment. I have to consider minus. Okay. What is the value of RB? RB is 1.5. 1.5 into 2 minus W. W is how much? 1 minus 1 into x square by 2. What is the value of x? X is 2. So into 2 square by 2. 3 minus 4 by 2. 3 minus 2, it will be 1 kilonewton meter positive. Bending moment at C will be equal to plus 1 kilonewton meter. So 1 kilonewton meter sagging bending moment. Okay, because it is positive, we will be getting sagging bending moment. Clear? Okay. Next question. I hope this is clear. Any doubt you can ask. Okay. Next question. Which of the following statements are correct? All load carrying members transmit load through basic modes of tension, compression, torsion and shear only. Tell me, this is correct or no? All load carrying members transmit load through basic modes of tension. Yes, tension, compression, correct, torsion and shear only. But they have written only. They transmit load by bending also. Bending, they have forgot bending. Okay, so when they have written only, that means nothing should be apart from this, but bending should also be included. So that means this option is wrong. This option is okay because bending is not included and they have written only, right? Next, beams carry transverse load. Yes, beams carry transverse loads. Sometimes they carry axial loads, but mostly they carry transverse load. So there is doubt here. Okay, only two options are correct. First, let us check other options also, and then we will see if this is it may be correct or wrong. So mainly beams are designed for transverse loads only. Sometimes axial load might also come. Okay. So let us see after checking other options, other statements, then only we'll comment on this. Okay. This might be true also. This might be wrong also. Okay. Now third, combined loading is a complicated loading. There is no clear-cut definition of complicated loading. What is complicated loading? What is complicated loading? There is no clear-cut definition for complicated loading. Okay. Combined loading may be considered as complicated loading also. Sometimes it might not be considered as complicated loading. So this option will say this is wrong. Okay, so when this is wrong, that means two options have to be correct. Okay, so 2 and 4 will be correct. But let us see fourth option also. Nature of internal forces decides the aspect of combined loading. Okay, whatever is the aspect of loading, combined loading, that is decided by the internal forces. Okay, so combined loading can be bending and torsion, bending and axial force. Okay, so it is judged by internal forces. What type of internal forces are generated, right? So we'll consider 2 as correct and 4 as correct. So correct answer will be 2 and 4. Correct answer will be option D will be the correct answer. Okay. Next question. Consider the following statements with reference to a continuous beam. So this is a continuous beam, not simply supported beam. Supported at A and C. So this continuous beam is supported at A and C. These two are the supports. Okay. So here, as expected, there is support reaction. Because of support reaction, there is a sudden change in shear force. Here also there is a support reaction. Because of this support reaction, there is sudden change in shear force. Okay. Now, at point B, can you say that at point B there is a point load? Because of point load also there is sudden change in shear force. At point B, we can say there is a point load. At point E also there will be a point load. Okay. So at these 2 points, I will be getting a point load. Point load at this point, point load at this point. Okay. Here I am having support reaction. This is support reaction. This is support reaction. Okay. Now there is no loading in this part. Why there is no loading? Because there is no change in shear force. Shear force is constant, so no transverse loading. Shear force is constant, no transverse loading. Shear force is changing gradually, linearly. That means in this portion, it will be a UDL. Okay, so just by looking at the shear force diagram, this much information we can extract. Now let us see these statements. There is a concentrated load acting at point B. Definitely there is a concentrated load. Point load will be acting at point D. So first statement is correct. Second statement, a concentrated load acting at point D. At point D, no. Concentrated load is not acting at point D. Concentrated load is acting at point. Okay. So at D there is, from in this region there is UD. A uniformly distributed load acting on the portion C. In portion CE there is UD. This portion there is UDL. Yes, correct. So option statements 1 and 3 are correct. 1 and 3 correct answer will be option. Clear? Okay, let's move on to next question. Which of the following loads should be applied on a simply supported beam so that the shear force is constant throughout its span? Okay, shear force should be constant throughout the span. So how can we get constant shear force? How can we get constant shear force? So in order to get constant shear force, let us say this value is P. Support reaction is P. Okay, so there should be no thing anywhere, because if there is loading, if there is transverse loading, it will change the magnitude of shear force. So if this is plus P, then this will be minus P. Plus P, then it will be minus P. So shear force diagram will be like this. Shear force diagram will be like this. Okay, it will be constant. But how to get plus P and minus P here? Since there is no loading, okay, without any loading, can we get these support reactions equal and opposite? Yes. These two are creating a moment like this. Which type of moment? Anti-clockwise moment. So we will provide a clockwise moment here anywhere in the beam. Okay, so it will be in equilibrium, and because of this moment there will be an upward support reaction. Here equal and opposite downward support reaction, and because of this, now moment will not cause any change in the value of shear force. Because of this moment there will not be any change in the value of shear force, but because of this moment we are getting support reactions, and because of these support reactions I will be getting this shear force. Okay, so which of the following load should be applied on a simply supported beam so that the shear force is constant throughout the span? So which type of loading should I apply? I should apply a concentrated moment anywhere in the span. Okay, UDL over the entire span? No. Two concentrated loads? No. A central concentrated load and UDL? No. A couple anywhere in the span. Couple or moment is same. Okay, so correct answer will be option. Clear? Okay, let's move on to the next question. A simply supported beam is subjected to a couple at a section within its span. Now, this question and this question, they both are similar to each other. Just the language is changed and entire question is same. So this was asked in 2013. This was asked in 2015. Okay. Simply supported beam is subjected to couple at section within its span. So this simply supported beam, it is subjected to a couple. Okay. Anywhere in the span. Okay, like this. So it will produce shear force diagram of zero magnitude. No, we have seen that shear force diagram will be of constant magnitude. Okay, shear force diagram, uniformly varying triangular bending moment diagram. So what kind of bending moment diagram we will be getting? So bending moment diagram will be like this. So uniformly varying triangular bending moment diagram. So bending moment diagram is, yes, in this portion if you say uniformly varying triangular bending moment diagram, correct. In this portion if you say uniformly varying triangular bending moment diagram, correct. But overall, can we say that it is uniformly varying triangular bending moment diagram? No. Okay, it is combination of two uniformly varying triangular triangles. Okay, combination of two triangles. Okay, but let us see, we'll see other options, then we'll decide on this one. Sudden change in sign of bending moment at the point of application of the couple. Sudden change in sign of the bending moment. Sudden change in magnitude and sudden change in sign. Okay, anyway, this we can say yes, this is correct. Equal and opposite reactions at its support. Yes, this is correct. Okay, so 3 and 4 are correct. So this will be considered as wrong. Okay, so 3 and 4 are correct. Correct answer will be option C. Okay, clear? Next question. 2013, 2014, 2013. What is a beam of overall length L with equal overhangs on both sides carries a uniformly distributed load over the entire length. Okay, so we are having, so this type of question almost everywhere, almost means many times this question has been asked. Same question is asked so many times. Okay, equal overhangs are there, UDL over entire span, many times you have seen. Okay, so a beam of overall length L with equal overhangs on both sides. So this overhang and this overhang both are same, equal, carries a uniformly distributed load over the entire length. To have now to have numerically equal bending moments at the center of the beam and at its supports, the distance between the supports. So earlier, this will be the bending moment diagram. Okay, so at this location, bending moment will be this. At this location, bending moment will be this. At center, bending moment value will be this. Okay, this is bending moment value here. This bending moment value here. This is so this bending moment value, this bending moment value, this bending moment value. These are numerically equal to each other. Okay. Now, in order to have these values numerically equal to each other, we have seen, and I have told you, you have to remember the result. This length will be 0.207 L, 0.207 L. If L is overall length, okay, this value will also be 0.207. So this remaining length will be how much? This remaining length will be 1 minus 0.27 into L. This will come out to be 0.586. 0.586 L. This will come out to be 0.586 L. Correct answer will be option here. Correct answer will be option C. Right. Next question. The bending moment diagram of a beam is shown in the figure. This is the bending moment diagram. Bending moment diagram. Shear force diagram is represented by. First of all, here bending moment diagram is linear. Okay, linear. 1 degree. Here bending moment diagram is linear. So when bending moment diagram is linear, and we know dm by dx is equal to shear force. So if bending moment diagram M is linear, that means M is directly proportional to x to the power 1. Right? Bending moment diagram is linear. Okay, and line, constant slope. That means bending moment diagram is directly proportional to x to the power 1. Yes or no? Okay, as the distance x is changing, bending moment is changing linear. Okay, so bending moment is x to the power 1, directly proportional to x to the power 1. Now, if I do dm by dx, that means shear force diagram will be constant. Okay, so if I do dm by dx is equal to v, that means will be okay constant. That means v will be proportional to x to the power 0. If v is proportional to x to the power 0, that means v is constant. So in this portion, shear force is constant, and in this portion, shear force is okay. So shear force diagram will be constant in this part and constant in this part. Okay, there is constant value, that means rectangular shear force diagram in this part and rectangular shear force diagram in this part. So in AC, shear force value will be constant, that means rectangular shear force diagram, and in CE, now here slope of bending moment diagram will be equal to shear force. Slope is constant, shear force is constant. Slope is positive, shear force is shear force is positive. Constant value of shear. Here slope is negative. Here slope is constant and negative. So shear force will be constant and negative. Shear force value will be constant and negative. This will be the shear. Okay. So here slope is constant and positive. Shear force is constant and negative. Here slope is constant and negative. Shear force value is constant and okay. So option A will be the correct answer. Option A will be the correct answer. Clear? This is the shear force. Okay. So for today, these are all the questions today. Let's meet in the next class. In today's class, we have done 28 or 30 questions we have done in today's class. And in the next class, we will do some questions. And our class schedule is every Tuesday, Thursday, and Saturday. Okay. Tuesday, Thursday, and Saturday. Every Tuesday, Thursday, and so Tuesday. In this week, Tuesday class is over. Let's meet on Thursday. So today's date is the date today, 23rd of May. So let's meet at 25th. Next class will be Thursday. We'll meet next class on. Okay. I hope understood all the questions that we have discussed in today's class. Let's meet in the next class on Thursday. Till then, bye bye. Take care.